Okay, so today I want to try an experimental lecture. So it is something which I have been reading up for the past 2, 3 weeks. And the topic which we are going to cover today is called Agentic Reinforcement Learning. So far, we have seen how RL has progressed through the last 50, 60 years. We started with classical reinforcement learning, where we looked at the algorithms of Monte Carlo, temporal difference, and then dynamic programming methods. And then towards 2014, 2015, we entered this era of deep reinforcement learning, and that mainly happened when the Atari paper came out. So people started applying reinforcement learning to tasks in robotics and video games. The main change which happened during that phase was that we could now represent our policy as a neural network, which previously could be represented in the form of a table. But it is impossible to represent all the states and their values in one single table. And people were always trying to experiment that can we represent the policy as a neural network. But until actually before the deep QN paper in 2014, there was a TD Gammon paper which came out in, I think, around 2000s, which also was a proof of concept where deep neural networks can be used to represent policy. And then after 2015, when people really started applying reinforcement learning to LLMs happened because the algorithm of PPO was invented, which was proximal policy optimization. This happened in 2017. And then people found that PPO algorithm is very well suited for using RL in LLMs. If you remember, that's the same time when transformers, the paper attention is all you need happened, and the parallel research was going on in the LLM space, and people also applied RL in LLMs. But the best application was through reinforcement learning through human feedback, which made sure that okay, you are pre-training a base model, that is fine, but how do you make the base model aligned with human preferences to behave like a chatbot, like humans interact with each other? So that is called as post training. And in post training, a crucial component was that of alignment, and reinforcement learning through human feedback played a big role in that. So the first chat GPT which came out in 22 December, it would not have been possible without RLHF, which at the heart of it had PPO, which had come out 5 years earlier in 2017. Then people understood that, okay, you are using PPO, and in RLHF, one of the crucial step is you have a reward model. So reward model is sort of like you pass in any kind of prompt and the completion, and the model gives you a score which rates how good or bad the completion is. And people train this reward model based on human preferences. And why is this required? Because if you have questions which are very subjective in nature, for example, if you ask me, do you like this poem or not? My answer will differ from your answer. So what people did was people uh, gave humans a preference between two options where they had to select their own preference. So, for example, if I'm given two poems, I can compare two poems. That is better than asking me to score for each individual poem. And then, based on these preferences which human labelers gave, a reward model was constructed. Now, this process was very expensive, like monetary expensive. It incurred millions or billions of dollars because it involved a lot of human labor cost. And it was not a, so only uh, high budget AI labs could do the RLHF process. Startups, people who do not have access to that kind of money had no idea how the RLHF pipeline works. Uh, the first paper which made this accessible to everyone was the paper which introduced this concept of using LLMs as a judge. So it basically said that you don't need human labelers to label the preferences, but you can pass it to an LLM, and the LLM can be used as a judge if you prompt it saying that you have this role and you have been given two answers and you have to rate one answer. So then people started using that. And the first LLM which performed well in that was GPT-4o. And then that completely revolutionized the RLHF workflow because it suddenly made that accessible for everyone. So even smaller AI labs could now align their models to human preferences because they could use LLMs as judges. Uh, okay, so this is also called as RLAIF, which is reinforcement learning through AI feedback, because there is no human in the loop anymore. Now, okay, fine. So we have gone from PPO to RLHF to RLAIF, but in 2025, one more thing came out which was GRPO. The main problem with PPO is that you need a critic model which is very heavy. It takes a lot of memory. GRPO came and said that you remove the critic model from your pipeline completely, and instead of having a critique, you sample multiple responses and calculate the advantage from the relative rewards which these responses get. And that made sure that you don't need a very heavy critique model in the RLHF pipeline anymore. But they added one more interesting innovation was they introduced this reinforcement learning through verifiable rewards, which means that you use, uh, let's say, completions which can be verified, which do not even require a reward model. For example, mathematics, coding, all of these tasks there are objective answers. Either something is right or something is wrong. You don't need a human labeler or even an AI to give feedback on that. So essentially, their pipeline reduced the number of models from four to two. Now you only needed the base model, which is the main policy that you're trying to train, and you need the reference model so that you make sure that your model doesn't diverge too much from the reference model. So it reduced the number of models from four to two. So these were the stages which have happened when applying RL in LLMs. And in the last lecture, we actually looked at the entire GRPO pipeline. And we looked at some nice examples where we can transform a model into a reasoning LLM using the process of GRPO. Now the next frontier, which is very new, it has only started in the last 3-4 months, is reinforcement learning agents or agentic RL. The objective of Agentic RL is basically to use reinforcement learning to operate a set of tools and perform some tasks using LLMs. So, if you look at ChatGPT, Gemini, all of these now have a deep research mode where you ask any question and it takes some time. Sometimes it takes 10-15 minutes for the LLM to go through a bunch of documents and come up with the answer, which is usually very comprehensive. Now, behind the scenes, if you look at it, they have implemented agentic reinforcement learning. And the paper which I have referred for today's lecture, I am just going to share it with all of you. It is a very interesting paper. It is somewhat long, but many of the pages are taken up by the references. So actually, the paper is 50 pages long. It appears to be 75, 100 pages long. So it outlines the landscape of reinforcement learning in for LLMs. So I'll just start sharing my screen now. So this is the paper which I have shared with all of you. So this paper came out early this month, and all of the references you will see are mostly from this year only because, as I said, this is not a very old field. Basically, it goes through all the details and what exactly is agentic RL, etc. But today's lecture we have dedicated to this. And the reason I wanted to cover this as a last lecture of our bootcamp is because I really think agentic RL is the future. And my thinking is heavily influenced from this paper, which was written by David Silver and Rick Sutton, where they say that they have this interesting graph which says that um, up until now, we were in this era of human data. ChatGPT, for example, is trained on massive amounts of human data. But you can't rely on data anymore. You only have so much data at your disposal. So moving forward, we need agents who can rely on experience and not on data. Experience means that you have to try out different things, understand whether your trial has worked or not, and then iteratively improve. That is exactly what reinforcement learning does. If you remember the main agent environment interface, which we discussed in the second lecture, the agent gets observations, performs some actions, gets rewards, and then updates its policy based on the reward which it gets. That is exactly what we are moving into, which is the era of experience. And I think that this era of experience can also be represented in more technical words as agentic reinforcement learning. So today we are also we are going to look at we are going to understand this terminology. What does it exactly mean? And we are also going to take one practical example where I have implemented the agentic RL application for one specific use case so that we'll get some clarity with respect to not just the theory of this, but the practical application side also. Okay, so let's start with today's lecture. So the main idea of the field of agentic reinforcement learning is this ability to train an autonomous agent which is composed of the following set of abilities. The first is planning, the second is tool use, third is memory, fourth is self-improvement, reasoning, and perception. So we are going to look at some of these individual components in detail. There are some components which are not really relevant to us, so we are going to ignore that. For example, memory is one component which we are going to ignore. We are going to focus heavily on tool use, and we are going to focus on reasoning. These are the two main areas that we are going to focus on. Now, before we dive deep, let us understand what really are AI agents. Okay. So AI agents in simple words, let's say you are at point A and you want to go to point B. So to go from point A to point B, to for us to define that task to be an agentic AI task, we need two things. The first thing that we need is we need an LLM, which helps us to carry that task to go from point A to point B. And the second thing we need is a set of tools. For example, if you are asking the deep research chat GPT tool, let's say, let me show that. Okay, so this is the deep research. Okay, so I asked it that plan me a detailed itinerary for a trip to Spain. So it will ask me a bunch of follow-up questions. What are your travel dates, which cities? So this is, I want to go from a point A to point B. I'm using ChatGPT 5 as the LLM for this. And this LLM is going to use a set of tools. For example, one tool it might use is looking up some websites like web searcher. There might be a web searching tool. Then there might be a payment gateway tool, etc. So there might be a lot of different tools which this agent internally has access to. Currently, I'm not aware which all different tools does GPT-5 have access to. But then this is an example of an agentic task. Okay. I'm going from point A to point B and I'm using LLM and some set of tools to go from point A to point B. Now we are in the same framework, but we somehow want to understand where does RL come into the picture here? How can we use reinforcement learning to be able to do this task in an efficient way. So let's look at the first thing, which is tool use. So one thing which you will see in traditional AI agents example is that the tool which the agent is supposed to use is already defined. The LLM does not decide the pattern in which the tool has to be used. So let's say there are three tools A, B, and C. The LLM first goes to A, then B, then C, and then performs the action or calls the relevant tools in that specific order. But what Agentic RL does is that it enables the agent to autonomously discover when, how, and which tools to deploy. And this the agent will learn through a trial and error process. Initially, it might start with the order A, B, C. Then it learns that starting with A is not giving me higher reward. So I'll switch the order. Maybe I'll start with B. And then later it tries out C, A, B. So it tries out different variations and finally chooses the right order to optimize the reward. This is exactly the flexibility which reinforcement learning allows us. We can now just define the final reward and the agent will optimize the set of actions to maximize that reward. So we are going to look at some examples, some GitHub repos which have actually done this. So this concept is called as tool integrated reasoning or TIR. So let's look at the first repo, which is Deep RL, Deep Eyes. Okay. So you can see that this already has more than 800 stars. And the title is that Deep Eyes Incentivizing Thinking with Images via Reinforcement Learning. So let's see what they are exactly trying to do. Okay, so if you look at the question says, is the cell phone to the left or right of the backpack? And if you look at this image closely, the backpack is the one which they have marked in green. It's over here. And the cell phone is something which the person is holding in their hand, which you can see in the which you can see the person is standing right next to the door. So the answer should be that the mobile phone is towards the left of the backpack. Now, how this process is done is initially the question is processed through the large language model. So you take the question and you pass it through an LLM, and then the LLM understands this question and breaks it down into chain of thoughts. So chain of thought 1, chain of thought 2, and chain of thought 3. And then you can see that the LLM has some tools at its disposal. You can see this here. There is a zoom in tool which the LLM has used after this chain of thought. And after the second chain of thought, the LLM has used another zoom in tool, which you can see through this microscopic symbol. And then finally, it comes to the final answer. So the model decides whether to perform a second perception via zoom in or to answer directly. So now you can see here how the tool use is up to the hands of LLMs. We are not defining the tool use beforehand. The LLM decides, do I need to use the zoom in tool for the second time also, or the first time I'm using the zoom in tool, that is enough. So here I only have one tool, but the LLM is not deciding the order of tools here, but the LLM is deciding when to use that tool. So remember I had said the LLM here decides when, how, and which tools to deploy. So in this application, we are not deciding which tools to deploy, but we are deciding when the tool has to be deployed. So this is an amazing application where you are mixing large language models with some agentic capabilities, and you are making that process much more reasoning oriented by using reinforcement learning. So this is an interesting example. Let's look at another example, which is called retool, reinforcement learning for strategic tool use. Okay, so yeah, so what they have done is they have also done something similar. Uh, they have used tool augmented reinforcement learning to guide LLMs to optimal strategies for leveraging external computational tools during reasoning. So from their accuracy graph, you can see that uh, if you augment the agent with this tool integrated reasoning, suddenly you start to get much greater accuracy. And they have also made their repo open source. There are a few other examples here. There is 2RL, which is also tool integrated reinforcement learning. Maybe I can zoom in and show it to you what's happening. Okay, so here the question we are asking is that two parabolas are the graphs of the equation y equal to 2x square. Please give the value of k plus m. So first what it does is it invokes this code tool where it executes a Python code and it generates some answer, but it realizes that the output that it gets from this answer is probably not correct. So it goes back and it rechecks the steps. If you remember the DeepSeek R10, we had discussed an aha moment where the model learns to reevaluate its initial steps. This is exactly like that. So you don't get this behavior of re or evaluating itself without reinforcement learning. So whenever you see something like this happening, it's probably a sign that the pipeline has some reinforcement learning step in between. Then there is another tool which I could not find an open source repo for this. It's called as Artist, which is agentic reasoning and tool integration in self-improving transformers. So this research has been carried out by Microsoft, and this I think came out 2 or 3 months back. So the reason I wanted to show you all of this is because all of these are repos which have been made open source very recently. And this is a very ripe area for research. And for replicating these repos, understanding whether you're getting similar results to what the repo says, and maybe going one step ahead and doing better than what the repo has done. So this is the state of the art right now with respect to tool integrated reasoning. So I have just marked here a bunch of tools where we have already seen Artist, we have seen DeepEyes, we have seen Tool RL, but there are some other agentic tool integrated reasoning solutions also. Okay, so now if you look at it, these are all open source. For closed source, all of these research labs have come up with their own variants. This one, which I just showed you right now, this is OpenAI's deep research tool, Kimi K2, QWQ. Then this one I have not personally used. Even Gemini has a research agent, deep research agent. That one is pretty good. So all of these are tool integrated RL, which means the LLM is actually deciding which tool to use, when to use, and how to use those tools. So in today's class, what we are going to do is that we are going to replicate a very powerful example where we are going to just use one tool, but we are going to use that tool with reinforcement learning. And we are going to do an agentic RAG application with that whole pipeline. Now, we have seen the first application of agentic RL, which is in tool use. The second modality is reasoning. Now, reasoning is something we have already covered in the class. Uh, Broadly speaking, reasoning can be divided into fast reasoning and slow reasoning. And previously, before 2025, there was little connection between reinforcement learning and reasoning. But only when the DeepSeek R10 model uh, came out in the DeepSeek technical report, people realized that you could train LLMs to autonomously develop reasoning skills using the algorithm of GRPO. And then this is an example of modifying the weights of the LLMs using reinforcement learning and imbibing reasoning in the LLM. But there are some other techniques also which people use to induce reasoning. One of them is chain of thought reasoning. Uh, Another is zero shot or few shot prompting. For example, just adding a simple prompt like think about this step by step, or let's think about this in a step by step manner. Just using this forces the model to uh, output its completion by giving the chain of thoughts along with the final answer. So I have a complete lecture on this in the Reasoning LLM from Scratch series, which is there on YouTube. So you can refer to that. So broadly speaking, these methods are called test time compute methods. The reason they are called test type compute or inference time compute methods is you're not doing anything with the weights of the LLM. The weights are frozen, but you are trying to induce reasoning capabilities inside the LLM by doing some post-training techniques such as chain of thought reasoning or few shot or zero shot prompting. So this also works very well. So there are multiple techniques used to imbibe reasoning in LLMs. For us, we are currently going to focus on this first section, which is uh, reasoning imbibed by changing the weights of the model, by fine-tuning the model using reinforcement learning. So if you looked at this example closely, in fact, all of the GitHub repos which I showed you, uh, many of them use GRPO, and they get this pattern where the LLM learns to reason. For example, let me show you this repo which we are going to replicate today. This one also uses GRPO in the Agentic RAG pipeline. And you can see that in the answer, the LLM, there is a reasoning step here. There, like within the reasoning open and closing tags, you can see that the LLM is trying to think of something. So this happens because of the GRPO step within the fine-tuning process. So far we have seen two modalities of agentic reinforcement learning. The first is tool usage, and the second is inducing reasoning capabilities to the model. And we are going to look at an example which integrates both of this very nicely today. Okay, so the application of agentic RL, there are four main applications. The first is called as search and information retrieval. This is exactly the example which I showed you over here. And we are going to take a practical example in this same category today, which is search and information retrieval. The second is code generation and software engineering. The third is mathematical reasoning. And the fourth is vision understanding tasks. So let's try to understand the first one first, which is the search and research agents. So these search and research agents, there are two types. One are closed source agent and second are open source agents. So within the closed source research agents, you have all these famous ones: OpenAI's Deep Research, Perplexity's Deep Research, Google Gemini's Deep Research, Kimi Researcher, Grok AI Deep Research, etc. But no one knows the recipe behind these agents, exactly how they work. People know that they are using reinforcement learning somewhere, but no one really knows what is happening under the hood. And I wanted to show you this. 2 weeks back, there was this GitHub repo which was released called, I don't know how to pronounce this, so I'm calling it Tongyi Deep Research. So if you look at it, This is developed by the NLP team at Alibaba, and they have got 15,000 stars already. It was the most trending repository of the day. And the reason it's very famous is because to use this deep research tool in ChatGPT, you have to pay $200 per month, right? And these people have made the complete their code open source, and you see the kind of performance they are getting on all these tasks. Either they are comparable with uh, all these other tools, and in many cases they are even doing better. We can see that in humanities last exam they are doing better. Browse.com, they are not doing as better as OpenAI, but they are better than other models. So this is extremely good. So this suddenly means that you don't need uh, to spend that much money to get deep research done on your data. It also means that you can now run this locally on your computers. Why is that the case? This was because the base model they used is just a 30 billion parameter model, which is mind blowing, right? All of these models, for example, DeepSeek, they are 670 or 700 billion parameter models. So this is one order of magnitude less and equally powerful in terms of the capability. So I was amazed and I started to study their entire architecture, what exactly they have done. But people are discussing a lot because I really think that this is now going to become open source, and there is no need to pay such a high amount for using these deep research tools. If you can locally run it on your laptop, it will be amazing. So this is one of an open-ended research task for anyone who is interested. Uh, I really want to replicate this deep research repo. Some people have already started doing it because no one really knows if it is that good. People can share these preliminary results, but if we can compare it ourselves, then it's truly amazing. Now, the reason I'm showing you this is this uses reinforcement learning at the heart. You can see here they have an end-to-end reinforcement learning pipeline which is based on GRPO only. Most of these or deep research agents, open source especially, which are coming out, they are using GRPO because of the simplistic nature of um, the training process it offers compared to the PPO training process. Okay, so this is very interesting. And then there are many other GitHub repos which have come out. They are not as good as this, but they are probably a best way to start off if someone wants to replicate some repos. There is one repo called Search R1, then there is one called Deep Researcher. So these are also a reinforcement learning framework where the LLMs learn to reason and make tool calls in a coordinated manner. And you can see here that it is built upon the ideas of DeepSeek R10, where it showed that you can autonomously induce reasoning capabilities using GRPO inside LLMs. And we can actually take an example to understand this. So this is the output they get from this search R1 repo. If you ask the question, who is older, Jed Hoyer or John William Henry II, this is the ground truth. And first the LLM starts thinking, I need to determine if Jed Hoyer or John William Henry II is older. I'll search for their ages. So now what it does is, this is where it deploys a tool. So this is probably a Wikipedia search tool where these keywords are passed to the tool and this information is retrieved back from the tool. Career saves records. Okay, during his time he was also initiated. Like there is a lot of information which it retrieves. Now it again goes back into the thinking loop. It says, I found out that is a person. Now I need to find his age and compare it. So it again puts a search, gets information, then it finds out the date for this person, but it still does not have the date of birth for this other person. So it again searches, and then now it can compare and finally it can give the final answer. So you can see there is a loop which is running, right? So this is a typical loop which you see in AI agents, which is there is a TAO framework, think, action, and observe. So you can see a similar type of a loop here, but then this is also augmented with reinforcement learning. For example, there are a lot of actions you can take here, which can give you different rewards. The first intuition I have is here is the keywords that you choose are very important. So the reward is going to be sensitive to the kind of keywords I'm using within these search open and close tags. So the model will probably learn to identify good keywords as the training process continues to get higher and higher rewards. So even in today's demo, you can see that we'll aim to get something like this. It continuously goes into a loop and then finally it gives you the final answer. Okay, so and then yeah, this is another tool which is Deep Researcher, where they also have something similar. The question is, what is the name of the famous bridge in the birthplace of Gloria and D Major's composer? To answer this question, I need to figure out who Gloria and was and their birthplace. So it makes a plan. So this is again, it goes to the search, goes to the tool. Whatever you see within the search open and close tags, it is passed as an input to the tool, and then you will see the tool gives a response. So this is from Wikipedia, this is from some other website. And then from the search results, it concludes that I can see that Antonio Vivaldi is the composer and he was born in Venice. Now I need to find the famous bridge. So then it goes and it search famous bridge in Venice. It gets the response from the tool. So this is probably a web search tool because you can see the URL is, this is TripAdvisor, this is Wikipedia, and it gets more results and then finally it gives you the output. This is very similar to an agentic approach in LLMs, but now here the only difference is that we are using reinforcement learning to penalize tool calls which give bad rewards and reinforce tool calls which give good rewards, so that the answer is more robust and grounded in the truth. So yeah, so this is the first application of agentic RL, which is search and research agents. And I think now the community is going towards such a direction that this will definitely become open source in a very robust manner soon, as we already see from their results, this Tongyi Deep Research. The surprising thing is that why have they made this open source? People think that it's for altruistic reasons. They want to really uh, make sure that this code is available for everyone to replicate, but then some people feel that they have not really shared everything and they're probably hiding some things. So we will never know unless we try out ourselves, right? Okay, so now the second interesting application is in the code generation space. So this is the one that we are going to study briefly. So what is exactly code generation and software engineering? So basically, what we want to do is that we want to, let's say, there is some task which is given and you want to generate some code. Now, this is an ideal test bed for LLM-based agentic RL because you can actually verify whether the code works or not. So that's why there have been a lot of work in this space, and there are some good GitHub repos like Ace Coder and RLLM. All of these do not have that many stars, so I think people have not uh, made a lot of this open source, but I know by interacting with some people that code generation is of a high priority in a lot of corporates, and the pipeline itself is somewhat complex. The terminology they use for this is reinforcement learning through execution feedback, which means that you actually execute the code, you execute the GitHub repo, and you get the response from the execution. So you know whether uh, the repo works, or if the repo doesn't work, then you make some commits, you adjust the repo, and then it works. So you have a list of commit history in the past, which has transformed your code from version 1 to version 10. And all of these commits have received some reward. So you can basically train your LLM to say that I have gone from commit 1 to commit 10, and it passes all the test cases. Initially, it passed only one case. Now it passed all the 10 cases. So then you have to look at the difference in the commits between from commit 1 to commit 2, commit 2 to commit 3. And then those differences have to be assigned rewards, because essentially those differences is what allowed you to pass more test cases. So this is what is done in this code generation step. But again, this is a very open area of research. There is not a lot of work that has been done in this space. And then finally, there are two more applications which we are not going to discuss. The vision in understanding task is very interesting. Uh, there is there is a lot of demand for autonomous driving tasks nowadays. We were recently approached by a company where they wanted to develop a perception stack for autonomous driving cars. And Agentic RL is extremely ideal for such scenarios, because you are receiving a lot of information around you, and you want to process that information through a vision language model, but at the same time, you want to take action also based on the information that you are receiving by calling some tools. So you want those actions to be grounded in step-by-step reasoning processes, and reinforcement learning allows you to do that. So there are some GitHub repos. For example, we saw this Deep Eyes repo, right? This is a repo which actually comes within this category of vision understanding tasks. So we are not going to discuss this at the moment. Our primary focus is going to be on this first category, which is search and information retrieval. So what we are going to do is that we will take a short break now for 5 minutes. If anyone has any questions, you can put in the chat, and then I'll discuss them in today's class. After 5 minutes, we will focus on one practical example where we will build an agentic retrieval augmented system using reinforcement learning. So I'll share the GitHub repo, which we'll be replicating. Yeah, so just click on this, and I'll explain all the steps which are involved in this process after the break. Okay, everyone, let us get started with the next part of today's lecture. So first of all, I will just explain the objective of this project. What we want to do is that, let's say I have a search query. Let's say my query is, how many medals did India win in the Paris Olympics of 2024? I want to build an agent which can take that query, uh, decide whether to call a tool or not. If it decides to call a tool, I want to build a tool which is called as Wikipedia search. So that query will be passed to the Wikipedia search tool, and then I will get the most relevant answer to that query from the tool. Now, my LLM has more information along with the prompt. It has the observation which has been given back from the tool. Now what I will do is I will take the prompt and the observation again, and then my LLM will again decide what to do. So it will go into a reasoning process again. Then again it will decide whether to call a tool or not. If it decides not to call a tool, it will start thinking, okay, what should I do next? And it will keep on doing this until it gets to the final answer. So I have this loop, right, which is reasoning, search, observation. reasoning, search, observation. This loop I want to carry on until I get to the final answer. So now this is fine, and I want to do this entire process using reinforcement learning. That is my overall task, so that my agent learns how to reason better, how to search better, so that I get maximum rewards at the end. You might be having a lot of questions in your mind. For example, the first question might be, how do I develop this Wikipedia search tool? The second question might be, how will I develop the reward model? How do I know whether whatever output my LLM has generated, whether that gets high reward or it gets low reward? So there are a lot of questions which might come to mind. Another question is that which algorithm should I use? Should I use PPO or should I use GRPO? So we are going to look at this entire process in a very step-by-step manner. The first thing that we are going to do is we are going to build this Wikipedia search tool. And I'm going to explain to you how exactly that tool is built. I might take some words or terminologies that you might not understand, which is fine. That is not the goal of this bootcamp, but it will still help you to understand the entire process very well. Okay, so let's get started. The first step is to build a local search system implementation using Elasticsearch for Wikipedia data indexing and retrieval. So the first step which we are going to do is download the Elasticsearch engine. So let's look at Elasticsearch. So if you look at it, Elasticsearch indexing is the process of storing and organizing data in an index, which makes it searchable. So it's a very popular library which people use for searching bigger data and bigger documents. So first we have to download this engine. Then the next step is to download the Wikipedia data. So this takes around 20 to 25 minutes when I ran this code to download the Wikipedia data. And then the third step is to build this index, which is Python ES wiki build.py. So there are three steps: download Elasticsearch engine, download Wikipedia data, and third is building an index. Now, if you go to this GitHub repo, which we are going to replicate, all of this is included within this art search. So the first thing you should do is go to this, when you do git clone, cd change to this directory, and then run these commands. This is the first command, which first set of commands which you use to download Elasticsearch engine. Then you run this command which downloads the Wikipedia data. And then finally you run this command which builds an index. Remember, before you start running any command, you need to do this pip install requirements.txt so that all dependencies are installed. And then finally, when you do that, when you run Python wiki build, all you have to do is then later run Python wiki search.py with this query. So you will get the related output, which is the most relevant to this query from all this Wikipedia dump, which you just put here using this model scope download dataset. Now, when I was trying to replicate this repo, this was a point where it took me some time to replicate this successfully. And the reason it took me some time is, okay, so first of all, I was trying to figure out why exactly or where this information will be used. So if you look at this, right, .env_format, here we have to give these links, which is the Elasticsearch URL and the Elasticsearch password. And to do this, it is very important for us to build this Elasticsearch index in the first place. Now, if you go to this wiki_build.py file, you will you will realize that when the code runs successfully, the index will be hosted at this link, https localhost 9200. We are going to run it locally. And then you can set a password by running this command, which is export elastic password. So basically you have both the parameters which are needed in the environment file. But that was fine. The main problem that I ran into was uh, I was using runpod for running my code on a GPU. And when you are running on the runpod, as you can see over here, I was running as a root user. So when that happens, Elasticsearch does not give you the permission to build the index at a root level. So then what you have to do is you have to create a non-root user, and you have to follow some instructions to do that. So I have mentioned all of this in my GitHub repo, where I have cloned this and I have added in my GitHub repo for your understanding. But if you are not running as a root user, then I don't think you will have any issues running this at all. Okay, so that is the first step. All we have done here is that we have created a Elasticsearch URL, which just needs some search query. And then when you give that search query to it, uh, it will pass that query to this index, and it will give you the most relevant answer by searching through the index. Okay, so this is the first step, which is building a local search system implementation using Elasticsearch for Wikipedia data indexing and retrieval. So this will probably take around an hour or so. And then, okay, this is the performing the search, which I have explained. Now what you have to do after that is you have to go to this file .env_format, and first of all you have to rename it to .env, which is also mentioned at the bottom here somewhere, that yeah, here. Before you start, rename this to .env and fill the necessary environment variables. So you need to fill the variables, which is the URL we have already discussed, and password also we have discussed. There are two more URLs that you have to fill. This is the OpenAI URL, openai.com/chatgpt/v1, something like that. And this is your OpenAI API key, which you should pass over here. Now, the question that you might have is, why is this LLM key needed? And we will answer that in some time. But to run the code successfully, you need to pass these four parameters. This you can keep empty. You can just delete or just keep it till this point equal to, and don't add anything afterwards. So you just need to fill these four values in the .env section. Okay, I hope the first part is clear, which is creating the local search index and making updates in the .env file. Now we come to the main part, which is understanding the GRPO training loop itself. So if you look at this repo, we are going to go to SRC, and we are going to go to models, and we are going to go to trainer.py. And this is the code that we are trying to understand. So first we will understand the GRPO training loop. Okay, so the first step in the training loop is to generate the completions. What does generate completions mean? Basically, you pass a set of prompts to the LLM, and you ask the LLM to generate answers based on that prompts. And then you collect all these answers together. So that is exactly what we are doing. The first step is you tokenize these prompts in this step. Okay, tokenizer into bracket prompts, and you collect that in this input fields. And from that you create prompt IDs and prompt mask. Now, why do you need to create prompt mask? The reason you do that is because uh, let's say you are tokenizing tokenizing a specific prompt, and because you want the total length of the number of tokens to be a specific value, you add a padding value of 0 to fill those numbers. And you need a prompt mask because you need to tell the LLM that if we are padding, then the padding does not mean anything. Don't focus on the padding. So the attention mask is just something like you give a value of 1 to all the tokens which are actually said in the prompt, and you give a value of 0 to all the tokens which are just padding. So you have these two entries, which is prompt IDs and prompt mask. Now we come to the most important line in this code, which is this prompt IDs dot repeat interleave number of generations. So what does this line do? Let's say I have two prompts. How are you? And the second prompt is, what is your name? And the number of generations is 2. So what this will do is that this will change my prompt IDs to how are you? How are you? What is your name? What is your name? So basically it will repeat the same prompt 2 times. And the reason why we do that is, if you remember in the group relative policy optimization, for every prompt, we need uh, multiple different answers, because that is what we are going to use to calculate the advantages. And to get the multiple different answers, we are sampling this same prompt multiple times and then passing it through the model and getting those different answers. So that is why you repeat for multiple generations, because that is exactly how the GRPO process works. Then what you do is you pass these prompt IDs, the attention mask. Maximum new tokens is how many tokens should the LLM generate maximum, and maximum length is the maximum completion length, which is the prompt plus the token. Do sample, we require this because uh, if we set sampling to be true, then for the same prompt, we will get different responses every time, which is what we need. Temperature parameter is important for us because to get diverse set of responses, we need the temperature to be slightly higher. We don't need it to be 0. Maximum generate iterations. We will come to this. This is different from these number of iterations which are required in the GRPO step. And this is use KV cache. I think we are going to set this as false. Use diversity sampling and diversity penalty. This is not very important. Okay, and then what we do is we basically compute the completion IDs, which is we take all the output from this and we only consider the outputs which have come after the prompt. Those are your completion IDs. And along with the completion IDs, we also calculate the completion mask. Now, one thing which is important here is that you can see here that the completion mask is calculated by uh, calculating the start IDs, where we are identifying when does this observation opening tag appear, and end IDs, which identifies when does this observation closing tag appear. The reason we are doing this is because we want to uh, not include observation while we are running the GRPO training loop. So this is actually masked out. So that's why this is added separately in the in the completion mask. Remember, this observation is something which the tool is giving us back. So it is not something which the LLM is generating on its own, right? It is something which the tool is generating. So we don't need to include that in the LLM fine-tuning step. So again, notice the repeat interleave function here. This is crucial for the GRPO algorithm. And also notice that there is a mask applied for the tokens which come between the observation tags. So this is all the generating completions function does. Now we move to the next step, which is computing the log probabilities. Uh, Now this is something which we have been focusing on since maybe 4 or 5 lectures now. In all the policy gradient algorithms, you need to calculate the log of the policy, which is log of pi of AT given ST, which is what is the probability of taking an action when I am in a specific state. And for language models, we had discussed that this is something which can be done quite easily, because if you pass, let's say, prompt plus answer, if you pass the entire completion through the language model, for every token, you are going to get the probability of the next token. And from that, you have to choose what is the token which is selected. So let's say if the question is, where are you? Question mark, I am in India. So for the token where, I generate the logits for all the possible tokens in the vocabulary, and I calculate the probability for uh, the token corresponding to is, because the second token was is. And similarly, I do that for all the tokens in my sequence. And that is exactly what is done by this compute log probabilities function. It might appear a little bit weird, but if you go through it, what you will eventually understand is these input IDs, these are the prompt IDs plus the answer IDs, which are also called as completion IDs in this code, which is the entire sequence is passed in the model. And then what we are doing is we are calculating these outputs, and we are shifting these outputs by -1. And then we are passing these logits along with these input IDs to this log softmax function. So it ends up doing the same calculation which I verbally spoke about. And this is the log softmax function, where it takes the logits and it takes the input IDs as well. So what it does is that it calculates the log probabilities for all the logits. So first it does log probability f log softmax all the logits, and then just so this is like calculating the probabilities for all the tokens in the vocabulary, but we have to only choose the probability of the action which is taken in that state, which is done by this, which is index input IDs dot unsqueeze -1. So this is the step where the log probabilities are calculated, which appears in the GRPO formula. Now the next step is to generate the rollout data. Now, what does this mean? Let's focus our attention on this. We are calculating these old log probabilities and these reference log probabilities. So, why are we calculating two log probabilities? The reference log probabilities is needed because eventually we are going to calculate the KL divergence, and for this we need the reference log probabilities. The old log probabilities are needed because in the GRPO formula, which is a derivative of the PPO formula, there is a ratio which comes in, and the ratio is uh, current log probabilities divided by the offline or the old log probabilities, which is pi new divided by pi old. So to get that ratio, you need to calculate the old log probabilities in the first place. That is why you have uh, these two definitions. So this is actually the most important in this section. The rest is just we are passing these arguments. That's it. So it looks like a big function, but essentially these two are the main parts. And here you can see how the input IDs are passed to compute the log probabilities. We are actually passing both the prompt IDs and the completion IDs together. And then that's how we are calculating the log probabilities for the input output pairs. And there is a mask which is passed to this, which is if you see, okay, so K is the size of the completion IDs. And if you look at this closely, uh, there is something, yeah, so we are essentially only looking at the logits to keep, which are the number of completion IDs, which means that if I have a prompt, where are you? I am in India. I am only focusing on the I am in India part to calculate the log probabilities, which makes sense, right? Because you want the model to be fine-tuned, not based on the prompt, but only based on the output which the model is giving. That is why you do this minus log logits to keep. You take all the tokens which come after the prompt. So that is what is happening here. Okay, now we come to the main part, which is calculating the group relative advantages. And this is where you will get to know that we don't need the critique model anymore. So what happens here is, if you look at here, how the advantage is calculated, you take the reward, you subtract the mean, and you divide it by the standard deviation. And I believe they add a small number here because if it's zero, you don't want the ratio to become infinity. And this is exactly what we had discussed in the class, that you only need the rewards to calculate the advantage. You don't need the critique model. But the question is now, how do we calculate the rewards? That I will discuss separately. But the main conclusion from this is that you don't need the value function model anymore, because you have replaced that with this advantage formulation. And that is what makes the GRPO such an attractive algorithm for uh, these kind of agentic reinforcement learning tasks. And then finally, we come to this maximize GRPO objective, where you will see that uh, here we are calculating two numbers. The first is ratio into the advantage, and the second number is the clip function ratio 1 minus epsilon 1 plus epsilon into advantage, and we are taking the minimum of these two. And this is exactly the same as the GRPO objective function, which we had discussed in the last lecture. Let me just, I hope it's there here. Let's see. Yeah, if you see here, what we are doing is we are taking minimum of two quantities, ratio into advantage and clip into advantage. So here also they are doing exactly the same thing, ratio of two quantities. The first, a minimum of two quantities. The first is ratio into advantage, and the second is clip into advantage. Just a sec. Yeah, so let's see, is it exactly matching? So this SIR1 ratio into advantage, this is the first part. And SIR2 is clamp, which is also clip. Clip of ratio 1 minus epsilon 1 plus epsilon. So ratio 1 minus epsilon 1 plus epsilon, they have added this 1.5 factor, and then you multiply. So it's actually exactly the same. And then remember, we have this minus beta into KL as well, which is what they do here, minus beta into KL, and this is the KL divergence which they calculate. And then that's all. So then you just calculate the loss afterwards and minimize the loss by doing back propagation. So this is the main GRPO objective function, which is actually used in this GitHub repo. In most of the practical cases, you actually don't need to know exactly what's happening under the hood. For example, in the last lecture, we saw the unsloth code, right, where we converted a non-reasoning LLM to a reasoning LLM. There we simply used the GRPO trainer, but we did not see exactly how the GRPO trainer worked. But hopefully this gave you some confidence as to, okay, what is happening underneath is exactly the same as the formula that we have discussed. So nothing new or extraordinary is happening under the hood. Now the main question is that how are we calculating the rewards in the first place? So before I come to that, I'll just discuss the types of rewards. Okay. The first is the accuracy reward, which gives a return of 3 if the accuracy is good and 0 otherwise. And we are using an LLM actually to evaluate this accuracy. I'll come to how exactly the LLM is used. The second is the format reward. So you can see if it follows this reasoning, it gets zero point 0.2. If it follows backtrack, it gets zero point 0.2. If it follows summary, zero point 0.2. Search and answer, zero point 0.2 and zero point 0.2. So, and then here also similar kind of scores are given for all these different tags. And finally, you have this reward based on the RAG quality, which is the retrieval from the Wikipedia search. We need to give some score for that also. So there you can see here, they are using this LLM URL and LLM key, which we are providing in the .env file. And they are using this retrieval quality evaluator function. We are just going to look at that function now. But essentially, they are using an LLM to score the RAG rewards. Now, this is and then the overall reward is the calculation of C plus F plus R, which is the correctness score plus the format score plus the RAG score. And the retrieval quality evaluator is nothing but the entire observation tag is what comes in that tag is passed to the LLM. And you can see here, you can see the prompt also. Context relevance evaluates whether the retrieved contexts are pertinent to the user input. This is done via two independent LLM as judge prompt calls that rate the relevance from 0 to 2. The ratings are okay, higher score, okay, fine. And then the LLM is prompted with two distinct templates to evaluate the relevance of retrieved context. Each rating is normalized, etc. And then the accuracy, which was the first reward, that is evaluated by passing the LLM API key and the LLM base URL, and then using that to evaluate the quality of the answer. Okay, so this is how the rewards are calculated, and that's the reason why we have to enter these API keys in this .env file, LLM URL and the API key over here. Okay, and then finally you have this tool, which is the WikiRAG tool, which we have developed, and it will go through this search where you will see that the Elasticsearch URL and the password has been passed, and whatever output we get, that is collected and that is passed back to the LLMs, to the LLM. Okay, now, okay, fine. So this is how the GRPO training loop exactly works, and we have understood also how the rewards are calculated and how LLM is used as a judge to calculate the rewards. Now there is one interesting thing I observed, which I wanted to explain all of you through one visualization. Um, so the interesting thing which I observed was this. So within this, if you go to, utils, And within that, if you go to utils.py, not utils.py, train.py. Yeah, this is an important piece of code because it is telling you exactly how the model is outputting the response. So how is it going through the loop of reason, search, uh, and reason, search, and observation, how it is going through that loop. So that is actually mentioned in this code, but instead of going through the pieces of code separately, I thought we can do one visualization and understand it. So if you click on, let's say if I ask the question, what was the impact of Apollo program on technology, and click on start simulation. So first, what happens is this is past. What was the impact of Apollo program? And then it says to answer that, I need to know what technologies were developed. And then it goes through the search tag. So it will become much clearer if it completes through all the iterations. So let us wait for some time. So you can see that in every iteration, it is actually going through a search and observation. And now I think you can understand what these number of generate iterations are. I had told you that I will tell you later, but if you look at this maximum generate iterations, these are the maximum number of times the agent goes through the reason, search, and observation loop. So here that was set as 3, I think. So it went through the iterations 3 times. Okay, so now you can see what has happened in the final output. What was the impact of the Apollo program? To answer that, I need to know what technologies were developed. Then it went through the search loop the first time, or the search tags, technologies developed for Apollo program. This was passed to the Elasticsearch index, and the observation was retrieved. Freeze food, dried food, etc. The Apollo program's word innovation. Now, again, another search query was passed and another observation was retrieved along with the answer. And then this happens 3 times until finally we get the answer. I think here it has mixed up the answer and search tags in the last one. The Apollo program had a massive technology impact. Answer, search again, technologies, okay, observation. This is again search, observation, okay. So it is going through this search, reasoning, search, observation loop 3 times. And it has been instructed that uh, unless if you see an answer tag somewhere, then stop. If you don't see the answer tag, then keep on going through the loop. That is why it knows when to stop and when not to stop. So this is the code file which you see for this code file has been converted to this interactive visualization. And to understand this, you can actually go through this train.py file. So this is the file which tells the LLM to how should you think, how should you go through this uh, reasoning, search, and observation framework before you arrive at the final answer. Okay, so this is just a step-by-step breakdown. So what happens is that the process begins with an initial prompt. Let's say what was the impact of invention of the transistor on modern computing. The code enters a loop that can run for a maximum number of iterations that we have already seen. The model starts writing an answer it might generate to understand the impact. First, I need to know who invented the transistor, and then it gives a search. The search tag stopping sees the search tag and immediately stops the generation because it goes through the tool. The main function now looks at the text generated in step 1. A tool call is needed. The code finds the search block, it extracts the query, it calls the tool, which returns an observation, and then it appends this observation to the text, creating a new longer prompt. So now you have the search plus the observation. The code then loops back to the start with this enriched prompt, and then the answer is complete. After one or two loops, the model generates the final answer and appends the closing answer tag. The code sees this tag, marks this sample as done, and stores the final text. It will no longer participate in the generation loop. If the model generates text without any special tags and doesn't hit the end of sequence, the code simply appends the new text and goes back to the start of the loop to generate more. So this is the entire process, how exactly the code is being generated in loops. And that is how you see this, if you look at the repo, this is the kind of output. It's in Chinese, but I was able to, yeah, so this is in English. Which of the following is incorrect for biological examination of patients with dysentery? So first it goes through the reasoning, then it identifies the tool, gives an input to the tool, gets an observation back from the tool. It backtracks also here and then again does a search until it finally gets to an answer. And I replicated this actually. It works quite well for some cases, for some it doesn't. The main reason it happens is because this is one reward file which I generated, which has the average reward and the loss also. So you can see here that it's a there is a huge amount of variance. So just look at the blue curve, and on the right you see the markings. So in some iterations I'm able to get high rewards, but suddenly it drops down and I get low rewards, and it kind of fluctuates continuously. So I tried a lot of hyperparameter tuning to get this to a stage where the rewards monotonously, or at least you can see a trend for the reward increasing, but that didn't happen. And because of this, uh, I was able to get that loop, but it doesn't perform as efficiently as I would have liked. So I'm still experimenting with it, but I've got the main function and the main logic to work. But this is the hyperparameters which requires tuning. But yeah, I encourage all of you to try this. It doesn't require, you can use a simple A100 or an A40 also. It costs around $0.4 per hour on RunPod. So I use that for running this particular code, and it's a great entry into agentic reinforcement learning. Okay, so to summarize, today we learnt about agentic RL, and we also understood what is the application of agentic RL in the search and retrieval tasks. Uh, and in the coming months, you will see a lot of open source GitHub repos which have used agentic RL to make the deep research functionality more open source. But I'm very excited by the Tongyi deep research tool, which has performed very well compared to all the closed source deep research agents. And it only uses a 30 billion parameter Quen model, which is almost one order of magnitude less than all the other closed source models which are out there, which are probably using huge models to run the agents. Okay, so this is an amazing project, and this is something which all of you can replicate. And yeah, so overall, in the RL journey, you must have seen that I've tried to keep a balance between theory and the practical aspects also. And we have covered, I think, more than 10 projects overall through the entire process. All of the projects are uploaded in my GitHub repo, so you can execute that step by step. And since the last 4 or 5 lectures, we have mainly focused on RL in LLMs because I really think that is the future. And you will see a lot of organizations and labs using reinforcement learning in the months or even years to come as we enter the era of experience. Uh, okay, so that actually brings me to the end of today's lecture, I will share this notes and I'll update the README file on the GitHub repo so that whatever changes I have made when deploying the Elasticsearch index that you have to do if you are running as a root user. Other than that, I will really encourage all of you to replicate some repos to start off with in the Agentic RL space. This is a very good area if you want to get started with doing research in the field of RL. It doesn't require a lot of deep theoretical knowledge, um, but it also integrates a lot of practical knowledge which has been explained to all of you in the course.